Hello everyone, this video is to understand the standard model of particle physics in detail. Before that, let's have a quick recap of what we have understood so far. The standard model of particle physics talks about two things, fermions and bosons. Fermions are the particles that what matter is made up of. Fermions are further divided into two categories, that is leptons and quarks. Now, bosons are the particles that help cause the interaction between other particles. We know that there are four types of forces, strong nuclear force, weak nuclear force, electromagnetic force, and gravitational force. So bosons are the particles that help the different particles to experience these forces between each other. Gravitational force is the only force which has a theoretical boson that's called graviton. It is not practically proven yet. So we will have a look at bosons for the other three, that is strong nuclear, weak nuclear, and electromagnetic. So see here, the force, if it is electromagnetism, then the boson that is being exchanged is photon. The properties include that it acts over all distances, so no restrictions within the distance of the particles. It is experienced by charged particles. It binds atoms and molecules together by electrostatic interactions. When we talk about strong nuclear force, the boson particle that is exchanged between nucleons is called gluon. It acts over a very short range, 10 to the power minus 15 meter. Now, this is nothing but size of a nucleus. So we can imagine that why gluons work over short range, because they work only within a nucleus to experience strong nuclear force. Experienced by quarks only, we will have a look at the quarks in detail, binds hadrons and nuclei together. The weak nuclear force, the bosons that cause the weak nuclear force are known as W plus, W minus, and Z naught or Z0. It is experienced by all elementary particles like leptons and quarks, explains beta and other nuclear decays, can change the flavor and or charge of elementary particle. So we can imagine that when two charged particles are being attracted, then the particles are exchanged. Those particles which are exchanged are called bosons. Similarly, when two charged particles feel repulsion, again, it is due to the exchange of the bosons. Okay, and every single force has a unique boson. So photon is a boson only for the electromagnetic force. Gluon is a boson only for a strong nuclear force. W plus, W minus, Z naught is only for weak nuclear force. For the gravitational force, the name of the theoretical boson is graviton. So boson is the general word, and now every electromagnetic force has its own particular boson. Okay. Now let's have a look at fermions. We know that fermions are divided into two. As you can see, the fermions are divided into leptons and quarks. So let's have now detailed look at what leptons are. Okay, so leptons, always try to remember as lepton as three pairs. So in one pair, how many leptons will be there? Two. So in total, there will be 6 leptons. Leptons are the elementary or fundamental particles. It means they cannot be further divided. Okay, the most basic or the most common lepton that we know is electron. Okay, so that we have learned from year 9 about circuits and all. Electron, that is a fundamental particle. It cannot be further divided. Okay, so leptons are the simplest particle which are truly elementary with no hint of internal structure. They are only affected by the electromagnetic interactions, weak interactions, and gravitational interactions. The 6 leptons are, the name of the 6 leptons are electron, neutrino, muon, muon neutrino, tau, and tau neutrino. So you can imagine that for every matter, there is an antimatter, or for every particle, there is an antiparticle. So if electron is negatively charged, electron neutrino or just neutrino will be positively charged. Similarly, muon and muon neutrino will have opposite charges, and tau neutrino. Therefore, I say that these are three pairs of elementary particles. Three pairs. Always remember, whenever you talk about lepton, remember three pairs. Okay, and these are the fundamental particles. Other than leptons, we have seen that the fermions have another category that is called quarks. Quarks are just like leptons, another fundamental particle. Quarks cannot be broken down further. The only difference between quarks and leptons is that quarks cannot be found alone. They need to be in the groups. You will never found a single quark in the universe. No, it will always be paired up with one of the quarks or two quarks, depending on what it is forming. Okay? Quarks together, when they combine, they form hadrons. Okay? Quarks are thought to be elementary in the same sense as leptons. Protons and neutrons are made up of quarks. Quarks interact only using strong nuclear force. Strong nuclear force uses gluon. So remember that the boson that is used to interaction between quarks is gluon, and quarks only use a strong nuclear force. Quarks do not use weak nuclear force or electromagnetic force. They only use strong nuclear force. There are 6 different types of quark. They are also referred to as 6 flavors: up, down, strange, charmed, bottom, and top. And you can see in the bracket, I have written their symbols, what they are represented as. Okay, so up, down, strange, charmed, bottom, top. All right, so remember the 6 different types of quarks, also known as 6 flavors. Let's now have a look at how quarks combine to form proton or neutron or antiproton or different hadrons. The electromagnetic charge of quarks are all fractions. How to remember this? What is the charge of a proton? +1. Okay, and if I say that proton is a hadron that is made up of 3 quarks, so the sum of the charges of these 3 quarks should be come up to be +1. In order for that to happen, the electromagnetic charges of each quark will be in fractions. Okay, quarks have their antimatter opposites called antiquarks. Every single thing will have its antimatter, and they have opposite sign for all of their quantum numbers. In my previous video, I have also said that quantum numbers, think of it as an address. You need to have the spin, the charge, the angular spin and strangeness and bottomness of these quarks. These will, if you have everything, these will constitute as what a quark is, or which quark we are talking about. So for example, if you want to talk about my address versus your address, even if we live in the same area, it will have something different, maybe the house number or the street name or the postcode. Okay, so something will be different. So each quark, for different quantum numbers, something will be different for that particular quark. Okay, so for quarks and antiquarks, their sign is opposite. Quarks have the properties of baryon number, spin, charge, strangeness, charm, and bottomness. These are all a part of their quantum numbers or their address, if you want to remember it like that. Example, for a proton consists of 3 quarks, 2 up and 1 down. So the total charge of 3 quarks should be +1. And we have seen that the electromagnetic charges of quarks are all in fractions. So it can be 1/3, +1/3, +1/3. It's not like I'm just giving an example. Okay. Only strange quark has strangeness equals to +1. Rest all have strangeness equals to 0. So for example, if we talk about bottomness, then the bottom quark will have bottomness equals to 1. Rest all will have 0. For charmness, only the charm or the C quark will have a value of +1. Rest all will be 0. Hadrons. Hadrons, the Greek meaning is heavy or strong. Okay, these are subject to the strong interaction as well as to the others. Hadrons are composed of either 2 or 3 quarks. Hadrons which consist of 3 quarks are called baryons. Example, proton and neutron. Hadrons which consist of 2 quarks are called mesons. Example, pion, kaon, eta. Quarks have charges in fraction and their combination in hadrons is always such that the hadron charges are either 0 or 1. Because if we talk about neutron, then neutron has 0 charge. So whatever quarks neutron consist of, their combined charge should always be 0. Hadrons continued. So hadrons are affected by strong nuclear force. They can be further divided into baryons and mesons. Example of baryons are nucleons, that is proton and neutrons. And there are some other baryons as well like lambda, sigma, xi, etc. Mesons consist of only 2 quarks. Examples are pions, kaons, others. Quarks have never been observed outside of hadrons. As I said, that quarks cannot be seen alone. Hadrons are divided into baryons and mesons based on a property called baryon number. We'll have a look at it now. Now, what are baryons? For baryon, the quantum number, which is very specific, is baryon number. That should be +1 for matter and -1 for antimatter. Sorry about the spelling mistake here. It should be antimatter. In this group of baryons, we have proton, antiproton, neutron, antineutron, along with hundreds of particles and their antiparticles such as lambda 0, anti-lambda 0, sigma plus, sigma minus, sigma 0, xi 0, and omega minus. Now you will say that sigma plus, the antiparticle is sigma minus. What about sigma 0? So some of the particles have themselves as antiparticle. They are their biggest enemy, let's say. So sigma 0 is the particle and it acts as antiparticle as well. Baryons consist of 3 quarks. For example, proton consists of UUD. Neutron consists of DDU. Now, charge of U quark is +2 by 3. Charge of U quark again is +2 by 3. But charge of down quark is -1 by 3. So when you will add, you will get a total charge of +1 for proton. So this is how we determine that the proton has 1 charge depending on what is the combination of its quarks. Now let's have a look at neutron. The down quark has -1 by 3. Again, down quark has -1 by 3. The up quark has +2 by 3. So when you add everything along with their signs, the charge of the neutron comes out to be 0. Each of the quarks must have different color of red, green, or blue, and they must always bond together in a combination to give total color of white. For example, red, blue, green, if we are talking about anti-quarks or antimatter, then it will be anti-red plus anti-blue plus anti-green. Adding the masses of the separate quarks in a proton is less than the mass of proton. So for example, in a proton, we have UUD. Okay, add the mass of U plus add the mass of U plus add the mass of D. It will be less than the total mass of proton. This is because most of the mass of the proton is stored in the gluons that hold the quarks together. So imagine in a small circle, you have quarks, combination of quarks. Okay. Outside it, imagine a bigger circle where you can write gluon. Okay, that is what is adding, keeping them together, the quarks together. And gluons are also the particles that are making sure that strong nuclear force happens between these protons and neutrons. Okay, and this is all called hadron because hadron is nothing but combination of quarks. Now, before you guys forget, because, okay, so remember hadrons consist, can be divided into two, baryons and mesons. So we have had a look at baryons. Now we will have a look at mesons. Mesons are particles that have baryon number of 0. So if we have baryon and meson, then baryon can have a baryon number +1. That's the quantum property. Remember address. And anti-baryon will have -1. But meson will have 0 baryon number. Meson consists of pion, antipion, pi 0, kaon, antikaon, and eta. So pi 0 is antimatter of itself. Eta is an antimatter of itself. Mesons consist of a quark and antiquark pair. Now always remember, baryons consist of 3 quarks, UUD, DDU. Okay, I'm giving you example of proton and neutron. When we talk about mesons, mesons consist of only 2 quarks. So one will be quark, one will be its antiquark. Charge of a meson is always either 0 or ±e. Okay. Quarks pair up in colors such as red, anti-red, blue, anti-blue. Okay. 2 for mesons. A quick summary of elementary particles. Matter and antimatter, that is fermions. Force particle, that is bosons. Fermions is again divided into 2 parts, quarks and leptons. Quarks combine to form hadrons. Hadrons divided into again 2 types, baryons, that consist of 3 quarks. Mesons consist of only 2 quarks. The bosons, those are responsible for the forces, are called gluon, W and Z, photon, and graviton. Always remember that graviton is a theoretical one. Okay? Thank you.